Now the linear polynomial, let's see what the zeros of the linear polynomials would be as a general case. Now for example, I take the linear polynomial in general form, then that would be a linear polynomial when written in the general form would be p of x equal to ax plus b, where a and b are constants and a is not equal to 0. They are real numbers. Now using this linear polynomial, I would like to find the zero of this linear polynomial. As a general case, I'm going to derive the general formula for zero of this particular polynomial, the linear polynomial. So to find the zero of a polynomial, p of x equal to 0 is what we consider to find the zero of the polynomial. Then we generate the value of x, which would give me the values for which are called the zeros of the polynomial. So when I equate this to 0, implies I equate the whole of px, which is ax plus b, equal to 0 on the whole. Now when I extract the value of x, I understand here that my x will be negative b over a, so that this value of x is the zero of the polynomial, which is the linear equation, negative times b by a. This can also be read as negative times the constant term, because here b is the constant term in the linear equation, negative times the constant term by a, which is coefficient of x, is how I understand the zero of the polynomial, which is linear. The zero of the linear polynomial is negative b over a, or negative times the constant term, whatever is the constant term, divided by the coefficient of x of the linear expression as given there, is how we understand the linear polynomial. Now before we go into this directly, if I wanted to say take an example to support this statement, then say for example I have a linear polynomial minus 3 minus 11x, then my zero of p of x is directly given as negative times of the constant term by the coefficient of x, which is negative 11, is how I understand using this formula. I get this. Then in this case, minus of minus 3 is 3 over negative 11, which is nothing but negative 3 over 11. And this is identified as the zero of the given linear polynomial, is how we understand. Now, how do we understand the linear polynomial in geometrical concept is very important, because balancing of algebraic approach with the graphical approach is very important in the topic of polynomials. So when it comes to the polynomial which is linear out here, then let's see how this polynomial can be identified on a graphical understanding. So for example, when I start with graphical understanding, let me consider now I would like to take an example linear polynomial to make the complete understanding of the linear polynomial on a graph, on xy coordinate plane, the real xy coordinate system. So therefore, let me randomly take one polynomial example which is linear. Say, let p of x is equal to 2x plus 4. Now this is a linear polynomial where when I compare with this linear polynomial, my a is 2, this is a and this is b. Therefore, my a is 2 and b is 4, is how I identify this linear polynomial respectively with a and b. Now, To understand this graphically, let me draw a table such that I take the different values of x and y. Say for example, I take the table which includes x and p of x, which I generally denote with y, because in xy coordinate plane y is generally denoted for p of x, and x is as it is taken in the variable on the right hand side. So x and px values are separately taken, and what I do in the linear form is first I substitute x equal to 0. So when x is 0, I want to know the value of y which yields from the given problem. So from this table, if I would like to fill this part off, then I substitute x equal to 0 in the polynomial. So let's see what will be the corresponding value of y or p of x for x equal to 0. So my working out here says when x is 0 implies y equal to p of 0 will be simply nothing but when x is replaced with 0 on the left, x is equally replaced with 0 on the equation there. So that is 2 times of 0 plus 4, which is 0 plus 4, and this is 4. And therefore, this value comes in here as 4. So this is the value which comes in place of this column and the row for corresponding x equal to 0. So this makes me understand that when x is 0, when the value of x is 0, the value of y is 4, is how I understand the second column of the table. Similarly, when the value of y is 0, I want to know the value of x out here. So how do we find? So I take the value of y as 0, that is y equal to 0 implies p of x is equal to 0, because y is equal to p of x. Therefore, when I took y equal to 0, then my p of x will be 0, but my p of x equal to 0 implies indirectly the whole of p of x is 2x plus 4. Therefore, this whole of p of x gets substituted with 2x plus 4 equal to 0, is how I get when I substitute in place of p of x. Then when I simplify this, I get this as minus 4. Plus 4 comes to the right as negative 4, and therefore I get 2x equal to minus 4. And then finally, I will find the value of x, which comes as x is negative 4 over 2, 2 ones, 2 twos. Therefore, x equals minus 2 is the value which comes out here. So I get this value onto this space. So this column makes me understand that when the value of y is 0, my value of corresponding x is minus 2. And this column says that when the value of x is 0, then the corresponding y is 4, is how I get the coordinates. Now I want to convert this into the real xy coordinate system, and the topic itself is about the graphical understanding of linear polynomial. So let's see how this polynomial can be understood on the graphical concept. Now continued with this, I would like to convert this table into set of points, because when I have px equal to 2x plus 4, the px being equal to y yields finally with y equals to x plus 4 is the polynomial the linear polynomial which we are considering out here. And for this, the corresponding points, I get them as usually in the form the point generally denoted by xy on the real xy coordinate system give me 2 points. One is 0, 4, because your x is 0, then y is 4. So 0, 4 is one coordinate which I get from the first column, and from the second column I get when x is minus 2, I get y is 0. So these are the two coordinates which I obtain in the second and the third column of the table. Now, as you assume these points on the real xy coordinate system, let's see how the shape of the linear polynomial would be by joining the points as obtained in the table. So let me take an xy coordinate system. and this is origin, and finally I take some random points here, 1, 2, 3, 4, and 5, and this is -1, -2, -3, -4. -1, -2, -3, -4, and this is 1, 2, 3, and 4, and 5, so on. Now in this case, this is y-axis, this is x-axis, this is y-axis, this is origin, and these are all the positive x values, and these are all the negative x values, positive y values and negative y values, and this completely makes the real xy coordinate system. And let's see how the shape of linear polynomial is in this xy coordinate system. In order to draw, first I take this point as A and this as point B and just plot them on the real xy coordinate system. So starting with point A, the point A clearly is 0, 4. Therefore, this point would definitely be starting from 0, x is 0 and y jumps to 4. So this is the coordinate A, which I identify here. This is the coordinate A. Similarly, -2, 0 is also being plotted. So I find that x moves -2, so -2 is here, and y unit 0, so therefore this would definitely be the point on x-axis. So here there is one interesting point we need to note, that when x is 0, the point lies on y-axis. When y is 0, the point lies on x-axis. It's a very important point which we use in graphical concept, and again I repeat twice, when x is 0, the point lies always on y-axis, and when y is 0, the point always lies on x-axis. Instead, this is called the y-intercept, this is called the x-intercept. So indirectly we understand that x-intercept is obtained when I substitute y equal to 0, y-intercept is obtained when I substitute x equal to 0, is how we understand the x and y-intercept concept in the real xy coordinate system, the graphical understanding. So once I get the 2 points, I just join them straight with a ruler, and then finally I get a straight line passing through that, and this straight line is nothing but the linear polynomial. I obtain a straight line joining the points A and B, and this line AB is nothing but the linear polynomial y equals 2x plus 4. So this is how we understand the linear polynomial. So a linear polynomial is a straight line passing through infinitely many points, and each point corresponds to the respective x and y value. Say for example, I want to find this point. Then here I understand that for x equal to -1 point approximately something, then my value of y is equal to 2, is how I understand the concept of x and y values. So a straight line with each point corresponding to each of x and y coordinate is how we obtain the whole straight line. So the learning outcome here is that a linear polynomial, whatever be the linear polynomial, in this case being 2x plus 4, but any ax plus b, a linear polynomial is always a straight line. Is how we understand. And if the graph cuts x-axis, the point at which the line cuts x-axis is called the x-intercept, and the point where the line cuts y-axis is called the y-intercept. In this case, -2 is the x-intercept because this line cuts x-axis at -2, and 4 is the y-intercept because this line cuts y-axis at 4. Is how I understand the x and y-intercept concept using the line. So the learning outcome here is that a linear polynomial is always a straight line. Now, as I identify here, -2 has also got some significance out here. Now coming to this previous problem, we have found the zero of the polynomial. The zero of the polynomial is obtained when I take p of x equal to 0. Therefore, the zero of the polynomial is the x-intercept of the graph. So this is also a very important note, that zero of a linear polynomial is nothing but the x-intercept of y is equal to x plus b. Is the x-intercept of the line y equal to ax plus b, or the linear polynomial. So the 0 and the x-intercepts are always associated because x-intercept is also called 0 of a polynomial. So I can also call the x-intercept as the 0 of a polynomial, or the 0 of a polynomial can be called an x-intercept. But ultimately, x-intercept is the intersection of line with x-axis. Also can be taken as a note. X-intercept is also called 0 of p of x, and that is nothing but intersection of. So x-intercept is 0 of p of x, and it is nothing but geometrically the intersection of y equal to ax plus b with x-axis. So the intersection of the line with x-axis is nothing but the point which is called x-intercept, or the 0 of the polynomial. Both are same, is how I understand the graphical concept of linear polynomial. So finally, a linear polynomial is a straight line on a graph. On similar grounds as linear polynomial, we will discuss now about a quadratic polynomial. A linear polynomial whose degree is 1 and a quadratic polynomial whose degree is 2 is what we're going to study in the graphical understanding of how the shape of quadratic polynomial would be. The shape of a linear polynomial is a straight line. The shape of a quadratic polynomial is what we're going to discuss here. So let's consider the quadratic polynomial. And the graphical understanding of quadratic polynomial is what we're going to discuss in the session. Now coming to the graphical understanding of a quadratic polynomial, let's take a quadratic polynomial. We all know that a quadratic polynomial is generally denoted in general form as ax squared plus bx plus c. Say for example, where the condition is that a is not equal to 0 and a, b, c are all real numbers. The quotient of this would not be 0, and hence we get belonging to real numbers. Is how I understand the graphical understanding, starting with general form. Now before we start with the graphical understanding, as in the previous session we have discussed that an x-intercept is the intersection of the polynomial with x-axis, and y-intercept is the intersection of the polynomial with y-axis. Similarly, it holds for any polynomial considered. So here my x-intercept is what I need to find before I graphically draw the quadratic polynomial. So x-intercept is intersection of this equation p of x. If I take this as y, this is the intersection of y is equal to p of x with x-axis, is how I understand the x-intercept. The curve, the polynomial, the quadratic polynomial which cuts x-axis, that intersection points are called x-intercepts. So similarly, my y-intercept is also in the similar definition, where intersection of this with y-axis. So when the polynomial cuts y-axis, then the points where the quadratic polynomial cuts the y-axis, those points are called the y-intercepts. Give us the y-intercept values. Therefore, in order to obtain the points where the graph cuts, the quadratic graph cuts x or y axis is what initially we are going to find. So let's take an example quadratic polynomial and identify how the x and y intercepts can be calculated for the quadratic polynomial, or for any polynomial the method would be the same. So therefore, to start with an example, let me take a quadratic polynomial y is equal to x squared minus 5x plus 6. Now this is a quadratic polynomial because the highest power here is 2 and it is a non-integral integer, non-negative integer. Therefore, this is definitely a polynomial with each of the coefficients being 1, minus 5 and 6, and the variable is x. So for this quadratic polynomial, taken as an example case, I identify that my first coordinate is 1, the second is minus 5, and the third is 6, and then finally I get this. Now, my first initial stage is to find the x-intercept. How do I find the x-intercept for a polynomial, any polynomial? Now, as we have seen, the definition of x-intercept here is the intersection of the polynomial with x-axis. Then clearly the points I obtain in the intersection would be when I substitute y equal to 0, because every point on x-axis is 0. The point on x-axis always is of the form a, 0, where y is always 0. Therefore, in order to obtain the x-intercept, I take y equal to 0, and to obtain the y-intercept, I take x equal to 0. So starting with x-intercept, I start with taking y equal to 0, because the rule says for x-intercept, take y equal to 0. For y-intercept, take x equal to 0. Is reverse way. So x-intercept, I take y equal to 0. So indirectly, I mean my y is nothing but whole of x squared minus 5x plus 6 equal to 0. Now this is where I want to find the factors or the zeros of the polynomial x squared minus 5x plus 6. So in order to obtain the zeros, first I factorize this quadratic equation where I get the factors x minus 2 times x minus 3 equals to 0 is what I obtain when I factorize this quadratic equation. And then finally I get the value of x, which is 2, 3. When each of the factors are individually equated to 0, I get the zeros of the polynomial to be 2 and 3. And indirectly, these are nothing but the x-intercepts. That is, the graph y is equal to this cuts x-axis at the points 2, 0 and 3, 0 is how I understand in the graphical concept. In the graphical concept, y is equal to the quadratic polynomial x squared minus 5x plus 6 is set to cut x-axis at 2 points 2, 0 and 3, 0 because I get 2 zeros of the polynomial or 2 x-intercepts, and these are the points where the graph cuts x-axis. Similarly, let's see the y-intercepts or the points where the graph cuts y-axis. So to start with the y-intercept, as I told with the rule, x-intercept implies take y equal to 0. Y-intercept implies I will take x equal to 0. To start with y-intercept, let x equal to 0. That implies the polynomial y equal to x squared minus 5x plus 6 is simply substituted with x equal to 0. Thus, this reduces to 0 squared minus 5 times of 0 plus 6 is how this gets reduced. And further simplifying this gives me clearly equal to 0 minus 0 plus 6, which is 6. Therefore, this is the value where the graph cuts y-axis. So graphically, I understand with this point that y equal to x squared minus 5x plus 6 cuts y-axis at 0, 6 because my x coordinate is 0 and my y coordinate is 6, which comes here. Here my x coordinate is 2 and my y coordinate is 0, which comes in the second place. Therefore, the graph cuts x-axis at 2, 0 and 3, 0 and cuts y-axis at 0, 6 is how I understand the x and y intercepts. So once I get the x and y intercepts, I randomly take few of the values picked up and then find the corresponding y values. I take some of the x values and find the corresponding y values as a tabular form. So let's see the table. So coming to the table of values, I just pick up a table, this consisting of x and y, which is p of x, and then starting with I randomly take some of the values ranging from negative to positive. Therefore, I start with -1, 2, 3, and 4, and -4, and I'll take the y values correspondingly for this. Now there's no rule that I have to take some fixed values. Randomly you can take any values which are near to the x and y intercepts. So always choose for x-intercepts and take the nearest values ranging between 2 and 3, or nearest to 3, outside of 3 or less than 2. So I randomly took some values which are near to 2 and 3, not too far. Do not take 100 or 1000, and then we cannot draw such a big graph with such a huge scale. So let's find the values of y corresponding to each of x as -1, 2, 3, 5, and -4. Now here I have already included two values x equal to 2 and 3, which are x-intercepts in this. So I can easily get these to be zeros, because when x is 2, y is 0. When x is 3, y is 0, because the x value of 2 gives me y is 0. X value equal to 3 gives me y equal to 0. So these two being zeros immediately give me the value as 0. Now next, coming to y, when x is -1, I would like to find the value of y. So x equal to -1 implies the value of y, which is x squared minus 5x plus 6, gives me x squared minus 5x plus 6, and this would give me 1. So when x is 5, I substitute x equal to 5 in the given polynomial. I get 5 squared minus 5 times of 5 plus 6, which is nothing but 6. Therefore, when x is 5, my y is 6, as found out here. Similarly, when x is -4, I just work out here. When x is -4, I get y equals x squared minus 5x plus 6. This, on further simplification, gives me 16 plus 20 plus 6, which is nothing but 36, 42. So my y is too huge, which is 42 on the left. Is how I obtain the values. So let me not take such a big value, but I would try to take -2 so that I get a very lesser value. So when I take x equal to -2, then this would be -2 whole square, 5 times of -2 plus 6, which on simplification gives 4 plus 10 plus 6, 20. Therefore, this value would give me the answer as 20. This is what I get as 20 for x equal to -2. Now with these 5 values obtained, each column giving a corresponding point, I'm going to plot that on the real xy coordinate system, and I get, when I join the points, I get the shape of the given quadratic polynomial. So let's see how the shape of quadratic polynomial would be when I plot these points on the real xy coordinate system. Now continuing with drawing the graph, let's plot these points taken with the first point as -1, 13, correspondingly for x equal to -1, y equal to 13 gives me the first coordinate, and then the second coordinate is 2, 0, and the third coordinate is 3, 0. The fourth coordinate is 5, 6, and the last coordinate is -2 times 20. Is how I took the different coordinates. Now in this case, I see that the lowest value of x is -1 and the highest value is 5. So my x-axis will have the scale ranging from -1 to 5. And the lowest value of y is 0. Of course, the lowest value here is 0 for x. For x is this. And the lowest value of y is 0. And the highest value of y is 20. So I need to take a bigger scale because 20 is the highest value. So the scale depends on the values you have in the coordinates.